so today is on counting methods. This isn't like how to count by twos or threes or anything. It's more in how many ways could you do something, right? So, right, let's say I chose 2 students from this room or 3 students to help me get some things from my car for some sort of event, right? How many ways could I choose the 3 students, right? If I were giving 3 roles, such as class president, class treasurer, class secretary, how many ways could I choose that? Is that the same as the number of ways I could choose a committee of 3 students, right? That's what this section is all about. This looks like a lot, but a lot of these kind of come at the same time. So the main thing that you use to figure out how many ways can something occur is the multiplication principle, right? All these other things flow from that. So you end up getting a factorial, right? You learn something called a factorial, and these things can be used to calculate the numbers of ways to do something. And then the factorial opens the gate to 2 different things, permutations and combinations, which are different. And you can use both of these to calculate the numbers of possible ways to do something, but you have to use the appropriate one, right? So the idea is, how do both permutations and combinations depend on factorials, right? And how do you know which one to use in a particular scenario, right? Which comes to this one. Being able to describe the differences between them will help you determine, right, which one to use. All right, so that's a lot of fancy talk here. But when we break it down, it will be pretty simple. So thoughts, how could we do this? How do we do this? This isn't hard. Yeah, that's it. All we do is multiply, right? You can think of this as a path, right? First, you have 9 doors you can go through, right? And then, like a tree, right? There are 9 paths you can go down. And then at the second level, for each of those 9 paths, there are 8 paths, right? Then there are 13. So you simply do you're making 3 choices. There are 9 choices for the first choice, 8 for the second, 3 for the third. So you do all that, and you end up getting, I wrote this number down earlier, but perhaps you already did it on your calculator, 936, all right, outfits. You can see, because you multiplied, these things can really increase quite quickly, right? Only a handful of choices are being made, right? So basically, when you have several choices to being made, you look at how many ways can each choice be done, and you simply multiply those numbers. It's kind of hard to say to write in a formula that doesn't obfuscate, but actually clarifies. But this is the multiplication principle. If you have, say, n choices to make, and the first choice, let's call that choice 1. There are m sub 1 ways, and there are m sub 2 ways to make choice 2, etc. The number of ways to make your final outfit, or whatever the hell you're doing, is the product of how many ways there are to make each choice, right? So for example, you can think about that in a tree diagram. Let me think about, how many ways can I get from A to C? Well, I could take lowercase a to get to B, and then once I'm at B, I have 2 ways, right? Regardless of how I get there, I always have 2 ways. So there's 3 ways I can get to B, and then for each of those 3 ways, there are 2 ways I can get to A. So that's 3 times 2, or 6 ways. You could also draw a tree diagram, right? There are 3 ways to get to A to B, right? Little a, little b, little c, right? And then for each of those, there are 2 ways. 1, 2, 1, 2, 1, 2. So there are 6 different ways to get to C, right? You could actually draw out a tree diagram. That's where the multiplication comes from. Obviously, it would be much more, this tree diagram would be really difficult to draw here, right? but you could do it and it would look the same. You've probably all done this. We're all good with the multiplication principle, right? It's pretty straightforward. So the trick, though, is like, how can you break down to things into choices when it's not as straightforward as the problem I gave you, right? And then there are a couple of different ways that this is done. What's a typical way? So let's think of an example that's not as clear as this, right? So we're going to solve this using the multiplication principle and hopefully notice something that we can generalize to a larger number of cases. So I got a small bookshelf, right? And I have 5 different books, right? None of the books have the same title. And I want to arrange them on the shelf. So the question is, how many ways could I arrange those books? So let's break this down, right? How many individual choices are you making, right? So for example, in the previous problem, we made 3 choices: which blouse, which shoes, and which skirt. How many choices are we making here? No, well, let's think. Okay, if you're actually sitting here doing this, I give you these 5 books, right? Give you these 5 books and I tell you, right? So Frank, you arrange them how you want. So first, you're going to have to choose which book to place first. So how many different choices are you actually making? We're making 5 choices. Is everyone following that when you arrange 5 books, you're making 5 choices? Now, the next part's a little bit more complicated. Well, there are 5 books. How many books, then, could I choose to put first? Everybody, let's do this together. How many? Okay. Now, granted that I've made that first choice, how many choices do I now have for my second book? Right? Because we have 1 fewer, and then it would be 3, 2, and then at the end, you would only have 1 option for your last book. So using the multiplication principle, the answer would be 5 times 4 times 3 times 2 times 1, which is 120. So there's 120 ways, right? So I could make that bookshelf, and if I give you 5 books, I could give you, and I said I arranged them, there are 120 different photos I could take, right? And that's just with a small number of books. We call this an example. We call this a permutation of 5 items because we have 5 items, right? In their books, they could be anything, right? Mathematically, it doesn't matter, and you're assigning some order to those 5. Here's something that's important to notice about a permutation, right? A permutation is like a set, but it's one where the ordering matters, right? So spelling is an example of a permutation because the ordering matters, right? All of these 3 words, all of these 6 words, although only one of them is an actual word that wouldn't be underlined, right? When your spell check, these are all considered different words, right? There are situations, and we'll talk about this later, where these would be considered the same thing, right? So let's say A, B, and C are different people, right? And let's say I'm inviting them all to a party, or they're all coming with me to some sort of event. Having ABC come with me is the same as having ACB come with me in that case, right? So there are cases where the ordering matters, and there are cases where it doesn't, right? So permutations refer only to those orders that do matter. Questions so far? So here's an example of where orders does not matter, right? Here's one where they would. Now, considering this, is there anything special about the number 5 where this principle applied to whether I was arranging 10 books, 2 books, 3 books? Could I solve it the same way? Getting a lot of blank looks. This is a pretty easy question. Could I use the same approach? Or is there something special about the number 5? No. So let's get to that then. Let's talk about that. So for that, you use something called a factorial. A natural number is a counting number. So we're talking 0, 1, 2, 3, 4, 5, all the way up to 10 or 100, whatever, right? So if I have n objects and I want to put them in a row, I want to assign them some order, there will always be n factorial ways to arrange them, right? That's what an explanation, that's how you read this. So if you read 5 exclamation point, that's not a very excited 5, right? It's not like 5, it just means 5 times 4 times 3 times 2 times 1. And that's the number of ways you can arrange 5 items. Notice, right? So, for example, in the previous one, we had 5 factorial was 5 times 4 times 3 times 2 times 1, right? 2 factorial would just be 2 times 1. 1 factorial would just be 1. Okay, now this is weird. Does this seem wrong to anybody? Because if you're multiplying numbers, we feel like when you multiply 0, you always get 0. So it seems like it shouldn't be 1, but let me tell you why that's the case. It's because the number of permutations of a set of n elements, right? I just mean by permutation, how many ways can I arrange n elements is n factorial. So it's kind of a weird question. But let's think about what I was saying with the books, right? So 0 factorial should equal to be the number of ways that I can arrange 0 elements, right? So let's say I want to have, I don't know why I would do this other than to illustrate this point. I arrange my 5 books on the bookshelf, right? Each arrangement, I take a picture. And then I put them in an album. How many albums would that picture, how many photos would be in that album? We just solved that earlier, everybody. It's 5 factorial, which is 120 photos. Now, let's say I have that bookshelf is still there, but I want to put no books on it. A bookshelf with no books is an empty bookshelf. How many different photos can I take of that empty bookshelf? Just one photo, right? This is what an empty bookshelf looks like, right? It's not 0 photos. There's still one unique photo. If I said, hey, here's a bookshelf with exactly 1 book on it, there would also be 1 unique photo, the shelf with the book on it, right? So that is why 0 factorial is 1. You're also going to see some other formulas. It has to be 1 because we're in some other ways, but we all kind of get why 0 factorial is 1. Right? There is one way to arrange no items. That's hard to imagine when you keep it abstract. But if you go to the book example, it helps because you can imagine, hey, there's also that shelf there, right? So it's not like I'm not taking a photo of, it's not empty space. It's a shelf with no books on it, right? That's why 0 factorial is 1. So we're going to be doing this with pretty large numbers, right? So luckily there is a way to do this on your calculator, which is why I had you have it out. They might be in different places in different calculators. I don't know what will happen if you type in 5 exclamation point into Google. It will probably get it. But if not, you can type 5 factorial and not write out the whole word if you don't have access to a calculator when you're doing it. So let me show you the menu for this. So here's your calculator. It's hard to see here. Right there is the button called math, which I find a strange button because doesn't all buttons on your calculator do math? Right? I think so. But you can use that, right? So you click math. You go to probability, and then option 4, you will find what we're looking for. So we found out that there were 5 such ways. So let's look at that. So I hit the number 5, hit math, scroll over to probability. That's what PRB means. Select option 4. That gets us 120, which is what we found out, right? Let's also see, we'll see that that confirms exactly what we think it is. That's 5 times 3 times 2 times 1. Notice it will define 0 factorial is 1, which is weird. That does not involve any multiplication, but just understand that there is one way to arrange no objects, an empty bookshelf, an empty bag, whatever. Okay, so I think factorial is pretty easy, right? You're arranging n objects, you use n factorial. But there's a lot more going on. So let's come to another example and think about how we might be able to figure out how this would be different. So same thing, I'm displaying 5 books. I have 5 books, right? But now instead of displaying all 5 of them, I'm displaying 3 of them, right? So I choose a book, right, to go first and whatnot. But this way, the order still matters, right? Because ABC is different than CBA. But it's going to be a little bit different. So if I'm only arranging 3 books, let's break this down the same way. So before we found that there were how many separate choices to arrange 5 books? 5. How many separate choices are being made in this case, everybody? Is it still 5 or is it fewer? And the number of choices, everybody, is 3. So let's figure that out. So we just need to figure out how many choices go into each of these. So at the beginning, there's still 5 choices that I could make for my first book. There's still 5, right? How many choices would I have for the second book? And for the third? Okay, instead of continuing, I'd stop here, right? So notice this is similar to a factorial, but it is truncated, right? So when you have some number of objects and you arrange some, but not all of them, you have a truncated factorial. And they have a specific way of talking about that, right? So notice when we were talking about a permutation of 5 objects, previously, if you're assuming you're permuting all of them, right? You only need to talk about one number. I'm arranging 5 books, 30 books, 1 book, 110 books, right? Here, there are 2 numbers that are involved here, right? I could just as easily ask you, okay, I have 20 books and I want to arrange 7 of them, right? So let's give you the notation for this. So this is also called a permutation because it's ordered, but you say it differently. So the way this book says it, it says 5 things taken 3 at a time. I don't like that because it implies that like I'm repeatedly choosing 3 objects. That's not really right. What it really means is I am permuting, right? We specify this number as 5p3, which means have 5 items, permute, right? Order 3 of them, right? Five p3 is 60. So that means if there are 5 objects, there are 60 ways to order 3 of them, right? So this first number we have referred to as n because it's the size of the element, and r is the number of things we're permuting. That's just the notation. So in this case, n equals 5, p equals 3. Notice here we had 5 factorial, but we permute, when you permute, we permute it. How many objects did we select here? We have to select from here. And how many of the 5 did we order? So it's 5 for both of them. So this was 5p5, which ended up being the same thing as 5 factorial, right? So that's the same thing, but we want to see that you can permute less than 5 of them. So let's give you how we could figure that out. Notice you won't have to do this, but I'm just showing you where this calculation came from. Notice this is a truncated factorial, right? So if I want to untruncate it, I would have to add times 2 times 1, but that would change the value, right? So if I multiply something, I can undo it by also dividing by that something, right? So notice 5 times 4 times 3 is the same thing as 5 times 4 times 3 times 2 times 1 over 2 times 1. These digits would cancel out, right? We all good with that? This thing on the top is 5 factorial, but notice the thing on the bottom, well, it's equal to 2, but it's 2 factorial, right? Likewise, if I started at 7 and I wanted to stop at 3, right, I would have the same sort of pattern, right? Notice that 2 is, right, I'm permuting 3 things, right? So I only multiply 3 numbers, which means if there's 2 more numbers, right, to get down to 1. So notice this is n. This is n again, and this is p. So that gives us a general formula for a permutation. Okay, so here's the formula, right? So notice it says R should always be less than or equal to n. It doesn't make sense otherwise. Or you can say if R, another definition is you could say if R is greater than n, how many ways can I arrange 10 objects from 5 things? Well, that's not possible. So you could just say, well, in that case, it's always 0. But let's just go with this. Is equal to this thing right here. So we would have ended up getting the same thing if we did this. So notice in this case, the number of ways to arrange a bookshelf of 3 books on a bookshelf given 5 items, right? Let's just see that that formula would end up giving us the correct thing. That's 5 factorial because n is 5. Change that. Do it again. That is correct, but I just want to include. Right? So notice this formula will give us the same answer, right, as just doing it by hand, right? Looking at each individual choice. Questions here? Okay, so let's show you how to do that on your calculator. So we calculated this a couple different ways. The first way was 5 times 4 times 3. That was easy enough because we only have to multiply 3 numbers, but you might have to multiply more. That gives you 60. The other way I said it was, wait, this is 5 factorial divided by 2 factorial, right? Put the 1 and 2 on the top and put it on the bottom to get rid of it. Let's see if that's the same thing. So that's 5, math, exclamation point, divided by math. Oops, I shouldn't have done that. 2, right? Make sure you go in the math menu not too early. That's also 60, right? But let's say you forgot the formula. Your calculator luckily has it built in there. So in that case, you want to do 5p3, right? So you do 5 math. Notice the NPR is right here. These all should give me the same way because they're all the same way of saying, they're all different ways of saying the same thing. They're all mathematically equivalent. Questions here? This is just a reminder of where it's from. Now, just look at this. Just turn and talk to the person around you. What does it mean to permute like a smaller set? What does it 5p3 mean, right? How is it calculated, right? And explain why this formula works. Does everyone kind of roughly understand what you're doing? You won't have to derive this formula. You won't even have to use it much since it's built in your calculator, but it's good for it not to be completely magical, right? So let's talk to the people around us about this, and then we'll come back together, right? This formula, how this example is different from the previous one, and what does it mean, right, to permute? What does 5p3 mean? Explain it to somebody who wouldn't know what that means. Well, that's what. So if I write 5 with an exclamation point, that means 5 times 4 times 3 times 2 times 1, right? Now, you're right. In this case, we don't do that. But it's good to, right? We defined what factorial is, right? Instead of having a new symbol for a truncated factorial, notice when we want to truncate our factorial, you can divide 1 factorial by the other one. So it's saying if you need to figure out how to do n like 5 choose 3, you can use the formula. Well, that's going to be 5 factorial divided by 2 factorial. Just imagine that was 150. It would take a lot to write out that whole thing. So it's good to have that notation. Questions on this? Okay, so this is another way. Anyone not still, I mean, maybe not like they understand I said it, but who wasn't convinced with my pictures, right, to say that 0 factorial should be 1? Who still thinks 0 factorial should be 0? Or maybe doesn't think it, but feels it. Anyone feel that 0 factorial should be 0? Maybe a little bit? Okay, let's say that you did. Well, before, right, when we chose all 5 books, one way was that was 5 factorial, right? The other way, that's 5p5. So those are the same thing, right? I said these two things are equal to each other, right? Does that make sense why those are the same thing, right? They're both, one's saying, how many ways can I arrange 5 items? The other one says, from 5 items, arrange 5 of them, right? How many ways? So they're clearly the same thing. There's nothing special about 5. So n factorial must equal, this is just a little bit of something, right? npn, right? But then let's use this formula here. Generally, these numbers should be a little bit smaller. So according to this formula, on the top, I should have n factorial. But in this case, r is the same thing as, so I should be dividing by n minus n factorial. So knowing that this is the truth, n factorial should equal n factorial. N minus n, though, is 0. This is only true if 0 factorial is 1, right? Does everyone see that that must be the case? So 0 factorial has to be 1. If it was 0, I'd have problems because then I would have a divide by 0 error here, right? Questions? All right, so there's not too much of that. All you have to know is what you're applying it to, right? So it was a while ago, right? I remember this. There was quite a chaotic Republican nomination, 2016. At the time there was Iowa, there were 12 different candidates. You don't quite rank, but there are some voting systems where you rank, right? It's called ranked choice voting. If any of you ever moved to Maine, this is how they vote in Maine, by the way, and in some other countries. So let's think about this. Is this an example of a permutation? Does the order that which you select the candidates matter in this case? Well, we're choosing a candidate to be our first choice, our second choice, and third choice. So the answer is yes, yes. Okay, so this is an example of a permutation. So we just have to figure out what are the right values, right? So n is the number that you're permuting from. What is n in this case, everybody? And r is? So our answer is 12 permute 3, right? And you could type that in your calculator and you would get a final answer. Let me just show you how to do that with the formula so that we're all good, right? So before, this formula was this, right? In this case, n is 12. N minus r would be what? N minus r, everybody, in this case is 9. Does everyone see that? I can write 12 factorial as 12 times 11 times 10. And I could write all the numbers out, but I could also just write, does everyone see that that is the same thing, right? Because 9 factorial is just compact for 9 times 8 times 7 times 6 times da-da-da-da-da, right? I chose to stop at 9 because now notice these two factors cancel out. And I'm left with 12 times 11 times 10, which is 1320, 1,320. And notice, this is the same way you would have done it if you just went through it. 12 candidates I can choose for first, 11 for second, 10 for third, right? Permutations are easy to do, but it's good to have this formula because we will need it later. But if I give this question you on a celebration, I don't need to see this. All I want you can just write 12p3 and then use your calculator to figure out what number that is. Questions so far? Okay. Now, as I said, the ordering doesn't matter, right? If I won a free trip to Hawaii and I got to choose 3 people to go, I could choose 3 of you, right? If I chose Manuel, Abby, and Frank, that'd be the same thing as choosing Abby, Frank, and Manuel, right? It doesn't matter what order you're choosing them in. So let's think about something like that. Let's see what's going on here. So before, teacher was choosing to arrange 3 of 5 books on a shelf. Let's do something that involves choosing 3 from 5, but maybe is different. Suppose instead of arranging the books, you choose 3 of the 5 to give to somebody else, right? Give to a fair. I'm going to take these books, right? Maybe I'll give them to Jack, right? How many different sets of books could I choose to give away to the fair, to Jack, whatever? So does everyone understand what this is asking? Do we think that the answer is again 5p3? Jolette, you're shaking your head. What do you think's going on here? So you don't think they're 60? What is different here in this scenario than the other scenario? Any thoughts? Something doesn't matter here that matters when you arrange them on a shelf. Yeah. The order doesn't matter, right? The order doesn't matter because, right, if I put 3 books in a bag, it doesn't matter. It's the same bag of books regardless of what order I put them in, right? So when order doesn't matter, that means our number is going to be different. And here's my question, right? Do we think that this number of ways is going to be more than 60 or fewer than 60 in this case? What do we think? Less, right? And let me tell you why it's less. Some of those orderings, right? ABC is the same thing as CBA, which is the same thing as et cetera, right? So if I made the list of permutations, some of those permutations represent the same set of books, right? So I would have to cross off the ones that are already accounted for. Just like when you're doing that intersection diagram, you have to do, right, to find A or B, you have to subtract A union B because that part is double counted. Now, things will be more than just double counted here. So let's suppose one of the books is a mystery, one's a biography, and one's a textbook, and the other two are something else, right? Right? If I'm giving these 3 books to Frank, right? Giving Frank the mystery, the biography, and the textbook is the same thing as giving the textbook, the biography, and the mystery, right? There are 6 ways to arrange these 3 books because 6 is equal to what? 3. How do I get 6 from 3? That is 3. Factor 3 times 2 and then times 1, right? This is 3 factorial. There are 3 factorial ways to arrange the books. So imagine I list all 60 ways to choose from before, right? To choose to order 3 books from 5. This particular set is not special, right? Mystery textbook, dictionary, right? It's just a special. Each set, in this case, so these 6 really represent one combination, right? One bag, right? So if I look at that list, each permutation will have 5 other permutations which represent the same set. Are we cool with that? Right? Because there are 6 ways to arrange each set. So everything in that set, every combination, right, where order doesn't matter, is counted 6 times because there are 6 ways to order something. We following here? A little bit, right? So if I divide that 60 by 6, I get 10 sets. 10 sets of books. So the answer is 10. Maybe if this way doesn't help, maybe think about it the opposite way. Suppose I told you the answer was 5. You would say, well, there are 5 sets. Each of those 5 sets has 3 books, right? So I can arrange each of those 5 sets 6 ways. That 5 times 6 is 30, but I know that there should actually be 60, right? So that can't be right. It must be 10, because 10 unique sets times 6 way to order those sets equals 60 permutations. We all kind of following here? You won't have to derive this, but I want you to kind of notice that, right? Notice 60 is the same as 5p3, and 6 is 3 factorial, right? And this is what we call a combination, right? Or a choice. So I would call this 5 choose 3 or 5 combination 3. This means this means choose 3 from 5, but don't order them, right? Do we get the distinction? Notice that equaled 5p3 divided by 3 factorial. So notice these numbers are the same, these numbers are the same, and this number is the same, right? Is there anything special about the 3 and 5 case? No, right? This would be true for any two numbers. So that gives us this, right? So we can generalize this to this formula here. The number of combinations, we'll see where this formula comes from, but it starts from what I showed you here. Is n factorial times n minus r factorial divided by n minus r factorial. That's what I had for permutations, right? The new factor is this r right here. So as I said on the previous slide, this is true in general. So this formula they have starts out with this formula, right? And this isn't something you have to memorize, but I want you to see where this comes from, right? I had 5p3 ways to arrange the 3 objects, right? But if I'm all counting the same objects but arranged differently the same, I want to divide by 3 factorial, right? This is the same pattern generalized. Does everyone see that? Instead of 3p5 divided by 3 equals 3c5, this is ncr is npr divided by r factorial. NPR, we already had a formula for previously, right? Well, let's get to that in a second. I can rewrite 3 halves as 3 times 1/2, correct? So I could rewrite this as NPR times 1 over r factorial, yeah? NPR, we know, is equal to this. That's something we already found. Combine it into one fraction. So notice, following this formula, and this option is also on your calculator. So we used 4 before, we've used 2, now we're going to use option 3 there. Let's just kind of show the same ways, right? So if I'm giving away 3 books out of 5, that's a couple of different things. Just plugging that in the formula, notice this is 5. N minus r in this case would be n minus r. n is 5, r is 3, so n minus r is, so this is 5 factorial over 2 factorial times 3 factorial, which is the same. If I use it, this formula right here, it's 5c3 equals so all of these things should be the same, right? So let's try this on our calculator, show that it's the same thing. So let's start with the form. So we want to figure out how many ways. So I want to do 5. Choose 3. How many different sets of 3 can I choose out of 5 items? That is 10. And where did that come from? Well, one way it came from is, let's do 5 P3. How many ways can I arrange 3 objects out of 5? But then if I want to change them to combinations, I'm overcounting by a factor of 3 factorial, the number of ways to arrange the 3 objects. So I divide that by 3 factorial. Notice still get 10. The other way is to use that formula, right? So when you're doing n, so if you forget it, right, the 2 numbers on the bottom when you're doing a combination should always add up to the number on the top, right? So that'd be 5 factorial divided by. Now here you want to be careful, right? This division sign is not grouping, right? You need to, since the 2 and the 3 factorial are both on the bottom, you need to put them in parentheses, right? To say that you multiply those 2 things before dividing them. Everyone get what I'm saying there? 2 factorial, 3 factorial. Those all gave us 10. Questions here? There's a lot going on, but you don't need to be able to do all of this. This is what I want you to talk to your partner about. Just kind of 2 points. How is a combination different than a permutation? And therefore, why do you need to divide the permutation by that r factorial factor to get the number of combinations? Those are just the 2 things I want you to talk about, right? And I'm not going to ever ask you to derive this. This is, again, background information for you to understand where I'm coming from. I could just say a combination is order doesn't matter. Permutation is that the order does. Here's how you calculate those on your calculator. That wouldn't stick with you, right? So answer those 2 questions. Everyone understand what I'm asking you to talk about? Okay, let's give that a shot then. Okay, so let's answer these important questions. The difference between combination and permutation is in a combination, what matters, what doesn't? What's the difference? In a permutation, the order matters. In a combination, it, right? So why are we dividing by the r factorial way? That r factorial, if the order doesn't matter, right? If you're counting each order separately, you are going to overcount, right? You are going to overcount by a factor of how many ways can each set be arranged, right? So that dividing by that extra r factorial, right? we're showing this, we're doing all the math, showing it where the formulas come from, but basically that's taking into account for that you're overcounting. So you have to divide that permutation again to account for the overcount, right? Now, I'm not going to ask you to do this every time. You can just use your calculator, but again, I think maybe other instructors are different, their pedagogy. I think that I shouldn't just throw something out there to you and just say that it's magic, right? Well, let's go through this. You can also think of some other interesting things. So I have a group of 10 students. A committee is being chosen to meet with the dean. How many 3-person committees are possible? Is this an example of a combination or a permutation? This is a combination, right? One committee, if I chose from this classroom, right? It could be Una, it could be Ulysses, and it could be Andrea, right? That would not be a different committee of having Andrea, Ulysses, and whoever I said was Una, right? That's the same committee, right? So the order doesn't matter. So the only question is what number goes in what part? So that's a C. And it's C, it's something, C something. What's the first something? 10. I have 10 objects, and from that I am choosing. Do we all get why it's 10C3, right? So all you have to ask is, okay, what's N, what's R, and is it a combination or a permutation? Now we can use the formula I gave you before, right? You could just throw this in your calculator, but again, I want to show you that the formula makes this easy. This is N so this would be 10 factorial over R in this case is 3, and the other factorial there is 5, 2. What's N? What's R? 10 and 3, right? So notice this is the difference of those two. So the other factorial is, everybody, I'm going to rewrite 10 factorial like this. Y'all comfortable about why I can do that? Because the 7 factorial just means continuing onward, right? I'm going to expand the 3 factorial, but leave the 7. These cancel out, right? Then you can even do this by hand without your calculator by using some tricks. That 3 goes into the 9 3 times, and this 2 goes into the 8 4 times, and of course 1 doesn't matter. So I have 10 times 3 times 4, which is 120, right? You can see this structure. If the order didn't matter, it would be 10 for the first person, 9 for the second person, 8 for the third person, right? But the order doesn't matter. So I would divide by, okay, I've overcounted by a factor of 6 because each set of person is in there 6 times because they're sets of 3, right? 3 times 2 times 1. So that's why I'm dividing by the R factorial, right? Again, you don't need to know that, right? But it certainly helps. Notice something interesting. This is a different problem, right? I got this. 10C7. 10C7 would start with what on the top? 10 factorial. And then there's an r factorial. The r factorial here is, and now the n minus r is, so isn't this going to give me the same answer? It's a little confusing. Why should the number of 3-person committees and the number of 7-person committees be the same? And here's the answer. I could have rewritten this question as, from a group of 10 students, a committee must be chosen to meet with the dean. How many ways can I choose 7 students to not meet with the dean? Does everyone understand saying choosing 7 to not meet with the dean is the same as choosing 3 to meet with the dean, right? So each combination, right? So if you have a set of 7, right? The number of ways to choose 3 and leave 4 should be the same as the number of ways to choose 4 and leave 3, right? So this works for combinations, right? This pattern does not work for permutations because there would be more ways to order the set of 7 than there would be to order the set of 3. Questions? Has anyone here ever been called to jury duty or been on a jury? No? You will someday, assuming you're registered to vote. Or I think in this state, they choose from driver's license too. So even if you're not, right, and you're a U.S. citizen. I was called for a jury once when I was in college, but I was registered to vote at my parents' address in Seattle and going to college in Houston, Texas. So I just sent that I was not there and I was excused. So that's my entire experience with the jury system, right? But the way that it works is, right, some large number of people are chosen, right, and they ask you questions. Are there any reasons you couldn't be impartial to this case, right? Maybe if the case involves a police officer, if you have a family member that's a police officer, they think you might be biased towards police officers, you'll believe them, right? The defense attorney might not want you on there. So they whittle that down into a smaller group, right? So let's say that 40 people show up in the room for jury duty and 12 of them need to serve on the jury. So the question is, how many different possible juries are there here? And the answer we can find quite easily. First off, is this an example of a permutation or a combination? Turn and talk, combination or permutation here? Does order of the jurors matter? This, everybody, is combination. All right, you guys got it. All right. What are the two numbers of interest here? 40, right? So using that formula, this will be, you could just type that in your calculator. Or this would be, what would be the two factorials down here? They would be 12 and 5, 7. Really easy if you just remember the formula. The formula is n factorial over the product of r factorial and, what's the other number? It's r factorial and n minus r, which in this case would be you could do some of the tricks. This is too much to do that with. So you could just type this in with your calculator. You end up getting about 5.5 billion. That is a lot of different juries, right? So if the order also mattered, it'd be more. right? Just to give you a sense, I believe this is roughly 75% of the world's population, right? This is just a coincidence, and the book doesn't cover this. Just notice that this would be equal to 40C28 because if I'm selecting 12 people into the jury, another way to think of that is I'm selecting 28 to not be in the jury, right? Each set of 12 jurors has a corresponding set of 28 non-jurors, right? So that's how this is going to work.